Hi folks, in this video I want to talk about using a computer simulation to determine the best strategy for playing a simple dice game. Not a very interesting game, I don't really recommend it. It's a little bit like Yahtzee, it's very much simpler than Yahtzee. Actually, it's even closer to another game that's called Risk Express, which is a version of Risk where you try to conquer countries with dice instead of, by throwing patterns of dice. You'll see in the game how this one works. So, very simple game. You have 8 dice, and your goal is to roll the dice repeatedly until you get a set of 3 sixes or a set of 4 consecutive numbers. And as soon as you get one of those sets, you can set it aside and then continue rolling the remaining dice to try to get the other set. Right? So you roll the dice repeatedly. Anytime you match one of these 3 patterns, you can set those dice aside and then continue rolling to get the other pattern. And the idea is, what strategy should you adopt in order to meet these 2 goals, right? To get these 2 different sets in the fewest number of rolls on average. The strategic considerations are, if you have a single roll in which you have both sets satisfied, you have both a set of 3 sixes and you have 4 consecutive numbers, which one should you go with? Because one of the rules in this game is you can only set one set aside per roll. Right? So if you happen to match both patterns, you can only set one pattern aside, and then you have to roll again before you can achieve the other pattern. So one consideration is, if you can satisfy both, which one should you go with? And another thing to consider is that maybe you ought to hold off on satisfying one of these goals, one of these patterns, until you've done the other. Maybe one of them is harder than the other, and therefore you should hold off on the easy one until you've satisfied the hard one, because it'll be much easier to get the hard one with the full set of 8 dice than with the reduced set. Right? So that's another consideration. So there's at least going to be 4 different strategies, and probably even more. If you think about it, obsessively, you can probably come up with even more strategies. But we're going to consider the 4 different strategies. Okay, first of all, let's get the basic plan for the simulation setup. So remember, the most basic thing to do is we have to decide what the attributes of the state will be in the simulation, right? So at every point in time in the course of this game, you've got a certain number of dice in front of you, and you're checking whether or not you've met either or both of those goals, right? And you also want to keep track of the time, how many rolls you've done so far, and how many dice you're currently rolling. So we'll have 5 attributes. Time, just be a number. It'll represent how many times we've rolled. A num, I'll just call it num, number of active dice, right? So initially we have 8 active dice, but if we set aside a set of 6 sixes, then we'll only have 5 left, whereas if we set aside a set of 4 consecutive numbers, then we'll only have 4 left, right? So we do have to keep track of the number of active dice at any point in the game. The current roll will be a list of numbers, right? The numbers that came up on the currently active dice. And we also want to keep track of whether we've met goal A and whether we've met goal B. Those will be Boolean variables. Their values will be either true or false. Okay? Then, as I said, when we think about the updaters, we have to take into account, think about 3 different things here. If both goals can be matched on a single roll, which one should we go with? Which one should we favor? And also, should we wait until goal A is met before trying to meet goal B, or conversely, should we wait until goal B is met before trying to meet goal A? Right? So because the first question could be answered in 2 different ways, and then we have to decide whether to, in addition, whether to wait for till A is met for B, or vice versa. There's really 4 different combinations of strategies we could use. Okay, so for each one of those 4 possible strategies, we'll have a separate updater, right? Because the strategy determines exactly how we're going to update our state, right? Exactly what actions we will take at each roll. And then when we have the 4 updaters, we can run the simulation with all 4 updaters and compare the results to see which updater and therefore which strategy performs best. So for the first updater, we'll say we'll do a kind of a greedy strategy where we don't wait for one goal to be met before satisfying the other. That we'll just satisfy the first goal that we're able to satisfy. Right? We'll just take the first one we're able to do, and we'll set those dice aside first. But we still have to decide whether to go with A or B if we can meet both of them on the same roll. So in this updater, we will prefer A to B. If we can meet both goals, A and B, we will meet A instead of B. But other than that, if either goal is satisfied, we will just go with that one if it hasn't been satisfied already. So the way the updater works is, of course, we just increase by 1, as usual. The roll is going to be n number of random integers, right? So we can use we'll be able to use a random integer function, right, to generate a list of n random numbers, where n is the number of free dice, active dice. Now, A met and B met, remember, those are Booleans that keep track of whether a condition has been met or not. If a condition was met previously, then it will still be met after the update, right? We don't lose one of our goals that we've met previously. By the way, this symbol here, this kind of this wedge symbol or V symbol, that's the mathematical symbol for OR. Okay, so I'm using that for shorthand here. So what I'm going to say is that A will be considered to have been met, right? The A met will be true if it was previously true, meaning that we previously satisfied that condition, therefore it remains true. Or if when we test the new roll, the new roll satisfies condition A. Now this is going to be a function we will have to write separately, right? I'm not going to include that in the updater itself. We will write a separate function that will just test any roll that we give it to see if condition A is true. Remember, condition A was that there were 3 6s. Okay. Now, similarly, B basically goes the same way, with one complication, which I'll get to in a minute. B met will be true if it was previously true. In other words, if we had previously met condition B, or if the new roll meets condition B. But there's one other thing we have to be concerned about. Remember that we're not allowed to meet 2 conditions on the same roll. Right? We're not allowed to set aside 2 sets of dice on the same roll. So we're only allowed to meet condition B if we haven't met condition A on this roll. Right? So we have to check that we didn't just set aside 3 dice for condition A, because if we have, then we cannot also meet condition B. Well, I'm going to use a kind of a little trick, maybe not 100% obvious, but the way to check that condition A has been met on this very roll, right, on the current roll, is if the old value of A met is different from the new value of A met, right? If these 2 values are different, that means we just changed the value of A met. It just went from false to true, and that means we just set aside 3 dice for condition A. But if the old value of A met is the same as the new value of A met, that means we did not just set aside 3 dice, and that means we can, if we're able, set aside 4 dice for condition B on the current roll. Okay, so what I'm going to do is, in order to check that we haven't already used this roll to meet condition A, we will check that the old version of A met is the same as the new version of A met. right? And that'll tell us we're able to use this role for condition B. And finally, let's update the number of dice. You may notice I just magically corrected this last line here. This is easy to do. We know that we have 8 dice total to work with, but if we set aside 3 6s, then we have to subtract 3 from 8, and if we set aside 4 consecutive numbers, then we have to subtract 4 from 8. So the updated number of dice will be 8 minus 3 if the A condition has been met, and minus 4 if the B condition has been met. Right? And we want to use the new values of those variables, A met new and B met new, because we want to go with the current situation. Okay, let's talk about these two functions, test A and test B. Right, so we have to write these functions in Mathematica. I just want to plan out how we'll do this. Neither of them are actually terribly difficult. The first one is particularly easy because we can just use the count function that's built into Mathematica. The way the test A is supposed to work is that we give it a list of dice, right, the current roll, a list of numbers, and we just want to check to see if there are at least if there are at least 3 6s in it, right? Then the condition A will be satisfied. So okay, that's easy enough. We use the count function in Mathematica. You give the count function a list and what you want to count. So we want to count the number of 6s in the list roll, the list of numbers rolled, and we just want to make sure that that number is at least equal to 3, right? So that'll be easy to do. Checking for condition B is a little trickier. Again, the way it's going to work is it'll be a function. We'll give it a list of numbers which represent the numbers on the dice that we just rolled, and we want to check to see if it contains either one of the 3 sequences, either 1 2 3 4, or 2 3 4 5, or 3 4 5 6. Right? If it contains any one of those sequences, then we're good, and it satisfies goal B, and we can set 4 dice aside if we want to for that. In order to make this a little easier to check, what I'll do is I'll simplify the roll. So the roll, for example, here's an example over here. The roll might have a bunch of numbers in any order. And the first thing we'll do is we'll delete the duplicates. So there's a built-in function in Mathematica that just deletes the duplicates from a list. So, for example, if this was our list of numbers and we delete the duplicates, we'll delete the duplicate 3 and the duplicate 2 and the duplicate 4, and this is what we get after we delete the duplicates. And then it would also be helpful in checking for these sequences if we sort the numbers into numerical order. So if I sort these numbers into numerical order, I get 1 2 3 4 6, and you can do that with the sort function in Mathematica. Okay. By the way, this @ symbol, this is just shorthand for applying the sort function to the result of the delete duplicates function. It means exactly the same thing as if I put brackets around this, right? So I could have just written, instead of writing the @ symbol, I could have just written this. Oops. I could have just written this. But sometimes it's easier to write the @ symbol rather than worrying about putting bracket at one end of an expression and then again at the other end of the expression. Sometimes it's just a little easier to write the @ symbol. And I'm funny that way. I'm lazy, so I often do that. So anyway, so the @ symbol is just shorthand for doing that. And now that we've removed the duplicates and sorted the numbers, this makes it very, very easy to see whether or not one of these sequences is contained, right? One of these 3 sequences is contained in the list. And we can see it's staring us in the face that 1 2 3 4 is indeed contained in this list. So this roll does satisfy condition B. Now, one more built-in Mathematica function we can use is called the sequence count. This one is so specific. It's kind of amazing that they thought to include this, but the way it works is you give it a list, and sequence count will count the number of times certain patterns appear in the list. So what I'm going to do is I'm going to set reduced equal to this sorted and version of roll after the duplicates have been removed. So after we've removed the duplicates and sorted the roll, I'll call that reduced, right? So that'll be a local variable. And then we just plug reduced into the sequence count function from Mathematica, and we check to see if reduced contains any one of these patterns, 1, 2, 3, 4, or 2, 3, 4, 5, or 3, 4, 5, 6. This bar here, this is basically it means or, but it's used in the context of patterns, right? So it means this is like a larger pattern that will match either this pattern, or it will match this pattern, or it will match this pattern, right? So it matches all of those patterns if any one of those occur. So we're just looking to see whether any one of these three patterns occur in the reduced list of the numbers in the roll. And you can see in this case, yes, the first pattern does occur. So the number of times this pattern occurs would be at least 1, and therefore this would be satisfied, right? The sequence count would be greater than 0. So that's how we check that condition B is satisfied. Okay, so now it should be easy to go through the other three updaters. They're just slight modifications of the first one. So the second updater, I'll call it pref B to A. So it's similar to the first one, except that whenever we have both goals met on the same roll, we're going to prefer B instead of A, right? So if we can meet the sequence of length 4 and we also have 3 6s, we would prefer to go with the sequence of length 4. But again, if either one of the conditions are met before the other, we'll just go with whatever one comes first. Okay, so this is pretty much the same, and really the only difference is in these two lines, and I just reversed the A's and the B's, that's all. We just reversed all the A's and the B's here as compared with the previous one, and that means that this condition that we haven't used B already, we haven't set 4 dice aside for condition B already, we can check by making sure that the old B met value is the same as the new B met value. That'll mean that it hasn't changed from false to true, so we have not set aside those 4 dice for condition B, and therefore, if we want to, if we're able to, we can set the dice aside for condition A. Next. Now this one, first A then B, this updater is going to very strictly enforce the condition that we can't satisfy condition B until condition A has already been satisfied, right? So we wait till A is met before trying to meet B. Okay, so first two parts of the update are exactly the same. The third part is the same as before, that A met will be equal to A met. In other words, if we met it previously, it'll still be true. We'll still consider it met. And alternatively, if it hasn't been satisfied before, but it is satisfied on the new roll, then we will mark it as a met condition. And now the difference here, the condition updater part 4 is actually simpler than before. Now we want to say that we will consider condition B to be met if it was either already met, in which case it remains satisfied, right? The dice are still set aside, or if it's satisfied on the new roll and it was not satisfied on the previous roll, right? If it was, if it was satisfied on the previous roll, right? If it was satisfied on the previous roll, previously, then it's okay to mark condition B as met if we're able to. On the other hand, if condition A had not been satisfied previously, then we would not want to mark condition B as satisfied because, right, we're waiting until A is met before meeting B. The updating the number of dice is exactly the same as before, except I have to correct that. I have to change A met and B met to new. These should be A met new and B met new. I will change that. Okay, here we are in Mathematica. I tested this stuff earlier, so that's why I've already got everything typed in. But let me just remind you what you're going to need to do for this is load the simulation pack. One way to do that is to type get bracket quote, double quote, click on File Browser, and then select Simulation Pack M, which I think is the version. Maybe I'll upload both of them. I'll put them both on Canvas, but it might actually be easier to just load simulationpack.m and close the quote and the bracket and enter that. Okay, good. So now it knows all the commands for doing simulations. So here's the state. Time, number, roll, AMET, BMET. Initially time is 0. We haven't done any rolls yet. Initially the number of dice is 8. Right? We start off with 8 dice, and that can be reduced as we go along. I just made the roll for the initial state empty. It doesn't really matter for the initial state. We will roll the dice for each successive time step. And of course, AMET and BMET are both initially set to false because initially we have not met either one of those goals. Also, because we're going to be rolling a lot of dice in this simulation, I thought it would be convenient to make this function roll n, which simply returns a list of n random dice rolls, right? So we just use the random integer function in Mathematica, and we want a random integer from 1 to 6, and we actually want n such random integers, right? So this will produce a list of n integers, each one going from 1 to 6. Oh, let me enter these into Mathematica. So the state, the roll function. Okay, now here's the updater. Time is just incremented by 1. The current roll will be roll n of the current number of dice, right? AMET will be updated by AMET or the new roll has tested positive for condition A, right? That we've examined the new roll and we see that it satisfies condition A. And we will write the test A function down below. One other thing to point out. Notice here I use 2 vertical bars. That's for logical OR. That's what you use in Booleans, when you're talking about true-false expressions. The single vertical bar is what you use in patterns when you want this pattern or that pattern, right? But I'm using the double vertical bar here because it's in a Boolean context where everything is either true or false. Okay, and then BMET is we update it by saying either it was true before or it's true on the new roll. The new roll has satisfied condition B, and again we will have to write this function down below. But we also have to check that we have not used the current roll to set aside dice for condition A. And we can check that we have not used the current roll for condition A by just noting if the old value of AMET is the same as the new value of AMET, right? That means that has not changed. We have not used the current roll to satisfy it. Finally, the updated number of dice will be 8 minus. We check if the new value of AMET is true. If so, we subtract 3 for the 3 dice we set aside for the A condition, and then we check whether the BMET, the new value of BMET, is true, in which case we subtract 4 for the 4 dice set aside for the B condition. And now the definitions of the tests are pretty simple. I already went through it mostly in the slides. So test A is simply, we simply count how many times the number 6 occurs in the dice roll. I'm calling the input variable dice here. I could have used roll; it wouldn't have mattered. But the input is supposed to represent a set of dice, right? So I'm just going to count the number of times that the number 6 occurs and check that number is greater, that count is greater than or equal to 3. If so, then this will return true. Otherwise, it returns false. Test B. As I said, what we do is we take the list of dice, right? The list of numbers that came up when we rolled the dice. We delete the duplicates, and then we sort it. That makes it much easier to look for the patterns we want. And then we use the sequence count function we apply that to the reduced or the simplified list of dice rolls, and we look for these patterns, either 1, 2, 3, 4, or 2, 3, 4, 5, or 3, 4, 5, 6. And we check that the number of times these patterns occur in the simplified or reduced list of the dice rolls is greater than 0. Right? In that case, condition B is met. Okay, let me enter these into Mathematica. So the updater and the tests, test A and test B. And now we can try this out. Now I'm going to use, I don't think I've used this before, I'm going to use the run till command. So it works in a similar way. You give it first a state that you want to start in, right, that the simulation is supposed to start in, and then you tell it what updater to use. So we're using the first updater, right? Remember, this is the updater where we will meet whatever condition comes up first, but if both conditions are met on the same dice roll and we have a choice, we'll prefer to meet A before B. And now here, the run till command works a little differently. The third input is the condition on which you want to stop the simulation, right? So you run it will run the simulation until this condition is met. And in our case, we want to run until both conditions A and B have been met. So until A met and B met are true. Again, we used a double ampersand here because this is logical and, right? So double ampersand is short in Mathematica for logical and. Okay, let's try this. Let's see. Is it working? Okay, so on the first roll, when time was 1, we rolled a 2, 1, 1, 2, 3, 5, 3, 6, 5, 5. Let's see. We did not get 3 sixes. It looks like we did not have a sequence of 4 consecutive numbers either, so both conditions remain false, and we still have all 8 dice because we haven't set any group aside to meet one of the conditions. Okay, so we roll again. 6, 4, 4, 6, 1, 5, 4, 4. No, still we haven't met any of the conditions, so we roll again. Now, we're getting a bunch of 4s. We got 5 4s, but that's no good for us, actually, rolling a bunch of 4s. It would be good in Yahtzee, but not in the game we're playing. Okay, so we roll again. It looks like this time, let's see, 2, 3, 4, 5, 6. 2, 3, 4, 2, 3, 4, 5. Actually, this has 2 such sequences, 2, 3, 4, 5, and 3, 4, 5, 6. So it certainly does contain a sequence of 4 dice. So yes, so we set the B met condition to true, right? Now, notice we do not have 3 sixes, so we don't have the option of setting those 3 dice aside. Having set those 4 dice aside, now the number of dice we have to roll is down to 4. We still have to satisfy condition A because A met is still false. So now we will roll the remaining 4 dice until we get 3 sixes. Let's see, how long did that take? Let's see, 1, 2, 3. Wow, we had to roll. Holy cow, we had to roll a lot. If you've only got 4 dice, it can take a long time until you roll 3 sixes, right? So all in all, it took 37 rolls before we were able to meet both conditions, right? So you could do that again. You could try it again, and it'll take. Oh, that time we did it quickly. We in this case we actually met condition A quickly, and then we had to roll a few more times to get condition B. But it only took 9 rolls altogether. Okay, so it seems to be working correctly, right? The simulation we set up seems to be working correctly. So now what we'll do is we'll gather some data. So I'll use the run till many command. Again, the first 3 inputs are the same as before. We give it the starting state, the updater, and the condition at which you stop, right, on which you stop. And then we tell it how many times to run the simulation. So I'll run it 1,000 times, and we'll call this data 1. We're going to have 4 of these datas, right? We're going to have 1 for each of the updaters corresponding to each of the 4 different strategies, right? Notice I put a semicolon at the end because I don't want it to print all of this. I just want it to store all those 1,000 results in the data variable. Okay, so let's run this. Okay, so it'll take a little while. You can see that in this case, when I ran it previously, it turned out that the mean number of rolls was 51. Wow, so this strategy does not seem particularly good, or at least, I don't know, maybe 51 is a good result. We'll see. But it does seems to take an average of about 50 or a little over 50 rolls. Let's see what happens this time. We're almost there. Okay, there we go. 1,000 simulations. Now let's see, what is the mean time that was required in all 1,000 simulations? This time it was 52, right? There's also a built-in function called histogram. Have I used this before? But you give it the data set and what quantity you want to look at the numbers for, and then you give it the range of values and the interval. Yeah, I think I have used this one before. So here's the histogram for the time, in other words, the number of rolls. I'll tell you what, maybe what I should do is go from... okay, yeah, maybe that's okay. Let's do this. Let's see. So in this case, you see there are a lot of... there are 103 rolls, 103 trials, right, runs of the simulation where we were able to get meet both goals in less than 5 rolls, from 0 to 4 rolls. And then there were another 134 simulations or runs where we were able to meet the 2 goals in between 5 to 9 rolls, right? And you can see the numbers go down, but this is a function where you can, look, there were 78 cases where it took at least 150 rolls in order to satisfy both conditions. So this is what we call a distribution with a long tail, right? Generally, the number of rolls is small, but there are a significant number of cases where the number of rolls is very long, right? So it has a long tail. So let's hope we find something better than that, right? That doesn't seem to be a very efficient way of achieving our 2 goals. So okay, so here's the next updater. Pref B to A. So this is exactly the same. We just reversed, basically we just reversed the A's and the B's in these 2 lines, right? So now again we will, it's a greedy strategy. We will take whatever condition comes up first, we'll go with that. But if both conditions are satisfied, we will prefer B to A. Okay? And again, the only difference is in these 2 lines, right? So enter that. If you're typing this at home, just copy and paste the previous one and just go through and change, reverse all the A's and B's in these 2 lines. Now in this case, again, we can test it. Let's see, in this case, let's see, this time it took 3 rolls, and then we were able to get a sequence of 4. Let's see, yeah, 1, 2, 3, 4, right? So we do have a sequence of 4 here. So B met was true, but A met is still false. We down to 4 dice, and now we keep rolling to get our 3 6s, and this time it took 19 rolls. Okay, so let's collect some data on this one. You'll see from my previous roll, my previous run of this simulation, that this one was even worse than the first one. This one, or only slightly worse, this one took about 55, an average of 55 rolls per simulation to get to meet both goals. Let's see. Let's wait a couple seconds. Maybe I'll reduce the number of runs next time. Also, this is going slowly because we do have to do 54 dice rolls every time, right? An average of 54 dice rolls every time. Okay, so let's see. So this time, very similar to last time, 54 and a half. Okay, next strategy. First A, then B. That is, first, that is, we won't satisfy goal B until goal A has been satisfied, right? So we're trying to get 3 6s, and only when we get 3 6s will we try to get 4 consecutive numbers, right? If 4 consecutive numbers come up first, we will ignore it. We will continue rolling all 8 dice in an attempt to get 3 6s, okay? And so again, this is very similar to before, just that this is very similar to the pref A to B, except on the second line, or rather on the 4th line of the updater, I've replaced A met equal AMET new with just AMET, right? We're just checking to make sure that condition A was previously met, and if so, then we're allowed to meet condition B on the current roll, but not otherwise. Okay, and again, we could test it. Let's see. In this case, is there a good example here? 2, 3, 4, 5, 1. Oh, here we go. 1, 2, 3, 4. Notice that this roll did actually satisfy condition B. However, because condition A was not yet met, we ignored it, and we did not set aside 4 dice, so we just continued rolling the 8 dice. B is still considered to be false, right? B met is still false, and we just keep rolling the 8 dice. And then finally on the 5th roll, we did get 3 6s, and so now we mark the A condition as met. A met is true, and now we reduce the number of dice to 5. And notice that now it only took a few more rolls until we were also able to get condition B. We were able to get a sequence of 4 consecutive numbers. Okay, I'm optimistic about this one. Let's see, this one might be a good strategy. Oh, and you can see from my previous roll, oh, the numbers are, yes, they're going quickly, right? You can see from my previous run of the simulation that the average was like 13.5. Yeah, so this time, what is it? Yeah, about 13, 14. About 14 rolls. So this seems to be a much better strategy for achieving the 2 goals. You can do it at an average of just 14, about 14 rolls of the dice. And this is the last one. This one actually isn't so good. This one also, I think, in fact, this turned out to be the worst one. If you wait until B is satisfied before trying to satisfy A, that actually gives you the worst performance of all 4 strategies, right? When I ran it earlier, I found that the average number of rolls was 63. So we've got some conclusions we can reach, right? It seems that the best strategy is this one, first A, then B. That was much better than any of the others. Second and third were pref A to B and pref B to A. I think pref A to B was slightly better than pref B to A, right? But they're both distant, second and third, compared to first A then B, right? So this is just an example of how you could use a simulation to determine the best strategy for achieving some goals. Now, of course, this is a very simple situation. It's just a very simple dice game. It's not even an interesting game, but you can see how you might apply this thing maybe to real games or even maybe to real life, like real business situations or something like that. And that's what I'll try to do in the next video. I'll try to do a business simulation to demonstrate how you can actually use this kind of thing in the real world.